Huh. Oh, you're here. Hello. Welcome to part 2 of the Spiderweb Generator. This is a technical walkthrough. It's less fun. I want to share with you that while I was making the Spiderweb Generator for probably at least 95% of the time that I was working on it, I had the TV show The Blacklist on in the background to entertain me, and I had an open Diet Mountain Dew in my co-pilot seat. And so for that reason, I'm gonna do this video wearing my ridiculous Raymond Reddington hat and with a Diet Mountain Dew. So let's dig in. The Spiderweb Generator is not very complicated as far as the web technology. It's an HTML5 document. It uses Bulma and it uses the HTML5 canvas to draw the spider webs. All of the drawing code was custom written, although there was use of one library related to polygon validation, and I'll get to that. So here's the application. The reason that I chose Bulma was that I got layout and components without having to learn anything. I could just briefly scan the docs and pick what I wanted. And so let's look at that. Here's the HTML page. It hot links Bulma, and then there have been some custom styles added. The spiderweb logo in the top left corner was made with this program. It was scaled down though, because you can't make a spider web as small as needed to fit in that corner with this program. All of the panels are in one HTML document, just that most of them are invisible and they're swapped in and out with the buttons that control the flow through the program. So there's the step 1 intro panel is here, visible. Step 2 panel is hidden right now, and so are all the other ones. There's also a modal dialog in here, which is a pop-up overlay that has different content. It's all built in and it's all hidden or shown using JavaScript. And so, for example, there's a message if the web is not got enough points to continue, if the hub hasn't been placed, if the radii are malformed, and so on. Mostly what we want to look at is the JavaScript. So we'll go up to the top where there are some constants that are used, and they're separated out here so that there aren't magic numbers throughout the application. My use of magic numbers is a technical term. You can look that up. It's when you have hard-coded constants in the application. It's considered poor style, and you should extract them, give them a name, and document their purpose so that if you need to add an easy way to configure them in a user interface, it's clear what that is. The extensibility is not the main point though. The main point is that you don't want hard-coded constants in your application because they tend not to have any documentation. about how they're chosen, and if somebody needs to find them to understand it, they should all be in one place. So these things are here. Upon review, I found that there is actually, I think, one or two uses of a magic number in here. But I'm going to forgive myself because I made this application in one furious marathon in my free time over the course of a couple of weeks. It was not intended to be of a professional quality, and there were many finalizing review and edit passes that I would have taken if this was going to be a professional quality application. As a hobby, I figured it works, it's done, I'm mentally exhausted, I'm going to move on. So next we have variables related to application state. Okay. Hub coordinates, spiral, okay. These are parameters for drawing the web. Okay, now we get easy handles for all of the HTML elements that will need to be either listened to or updated. Okay, so configuring IO controls here with sliders. Okay. Event handlers. Okay, so I've added a show and hide function onto HTML elements for just simplifying. There's a function to open a modal with the parameter of which class a modal to open, and that has to do with the messages that are multiplexed in that one modal. So there's only one modal, and you just tell it which message to show when you open it. Okay, close modal function behaves as you would expect. There are click handlers for the buttons such as start. When you're done with each step, you click the done button, and the transition between steps will have a validation whether the changes that have been made to the web are valid. You can go back as well. So for instance, transition 2 to 3, step 2 to 3, we'll call this function. There's no validation in that one. Oh, it looks like there is. So that's one thing, is the transition and the event handler. I didn't settle on a consistent system with regard to where to put validation, and that's another thing that was kind of beside the point. Really, this application was about the 2D canvas. The main thing that I wanted to learn was 2D canvas drawing. And so the rest of the UI stuff was kind of just furiously hacked out. And that's one thing that, what I mean is, there should have been event handler functions, data validation functions during each transition, and then UI modification code. And those should have been implemented consistently with regard to the separation of concerns. So there's major separation of concerns issues throughout the transition code. And I'm okay with that. That's kind of beside the point of this program. Also, really easy to fix. That's one of those things that is not really, it was beside the point. And so moving on, let's look at, as I made this program, the first thing that I did was HTML, basic page, and put the configuration and the canvas. And really I programmed this in the order of how it works. And so it was very like use case driven. Like, as a person looking at the page, the first thing you're going to notice is the general layout, and you're going to scan the elements. So that went in first, the structure of the page, and then the next thing was actually the introduction and instructions were added kind of after the fact, but I knew that the first step was going to be to place the hub, so that code was written first. And then when you go to transition to the next step, oops, here we have a warning that it's incomplete, which is correct. So going in order, we'll do this in order as well. We'll walk through this code in order. There are really 4 interesting things in this program. One of them is placing the points. One of them is the algorithm to determine whether a point is inside of a polygon. One of them is the algorithm to determine whether a polygon is convex. And the last one is the algorithm to draw the web when all is said and done. So let me now think through the point placement. When you click on the canvas, the application is going to determine whether you have clicked on an existing point. If you have, it is going to determine where the point is to begin with, and then it's going to let you drag the point. If you drag it too close to an existing point, it is going to revert to its original location. If you have dragged it to a wide open area, relatively wide open, it doesn't have to be too far away, but it has to be not immediately next to, and that's one of those constants, the distance between 2 points. Then it's going to update the point if it's in a valid location. If you have clicked on an empty canvas, then the application is going to wait until you let go. And when you let go, it will then determine, is this point too close to an existing point? If it is, it's not going to place a new point there. If it is not too close, it's spaced out enough, then it will place a point there. I should say that with the 2D drawing canvas, it's the top left up here that is 0, 0. This is the increasing x axis. This is the increasing y axis. So the maximum x and y value in terms of pixels will be at the bottom right hand corner of the canvas. This program converts all pixel coordinates, all of the canvas pixel coordinates, to canvas relative coordinates, which is a coordinate pair where the x and y values are on 0, 1. And so within that coordinate system, the top left of the canvas is 0, 0, and the bottom right is 0, 1. 1, 1. And the reason for that is that if you resize and or reshape the canvas by changing its aspect ratio, the points are going to remain, the shape of the web is going to remain congruent with the changes that occur in the canvas. Okay, so that's the point placement. This algorithm apparently has some artifacts. It was simple to make, although it worked shockingly quickly with regard to placing the hub and then dragging the hub. I thought I was going to have to fight with dragging. It worked okay. When the next step was introduced, which is placing the radii, that's when this parameter of considerations came in, and limit as well. Because when it was place the hub, it could just check, is the hub already placed? If it is, you can't place another point. Well, when you're placing the radii, you can place more than one. So the limit should be a parameter, and it is. The considerations list has to do with when you are placing a new point or moving a point, which points should be considered when determining too close. And so the hub, the list will just contain the hub. As implemented here, the considerations list will contain the hub. And what that means is you can place points and you can drag them as well. But when you're going to consider proximity, consider this list as well. But points in this list cannot be dragged or deleted, for that matter. Deletion is another thing you can do. So there were two kinds of points that this algorithm will consider. One of them is active and can be placed, dragged, and deleted. The other kind should just be considered with regard to proximity. And so that's sort of an artifact that was added on during the second step. So when we click to place the hub, we get a blue dot. We can click and drag it. And look, it works, by golly. Second step is to place the radii ends. And we can see here, if I try to drag this too close, it'll jump back. I cannot click and drag the hub. And so I can't place a point there. Let's go to delete one. That's a custom cursor. Oh yeah. Shout out to pixlr.com, Pixlr. I made that there. The reason that I like it is it gives you a clear picture of what you're doing. The red X is sort of violent looking. You can tell that you're going to delete something, but with an X, it's not clear whether you're going to delete the thing at the center of the X or in the top left. Not clear. So that's why I added this arrow on the outside, so that it's very clear that what's going to be deleted is just at the tip of the arrow, and that's exactly what happens. There goes the point. Goodbye. On this step, we have this documentation about placing radii ends. I'm not going to go into all that in this video, but I mean, we'll go into it. I'm just not going to read it. Here's the gist. The hub has to be inside of the radii, and the radii have to form a convex polygon. So this is the second and third interesting things about this program. The algorithm to determine whether the hub is inside the radii ends, I borrowed. It is an open source algorithm. It is properly cited. Here it is. I simply call this function and don't worry about how it works. I did some manual testing and determined that it does seem to work. I did not do any programmatic testing of it. I believe that it works. Based on the quality of the documentation and the fact that they licensed it, they have it on GitHub. And really, the risk of it failing is very low. This is not a system that anyone's life depends on, or realistically that anyone will ever use. Now, let's look at the algorithm to determine whether the polygons form a convex. Whether the radii endpoints form a convex polygon. That's what we're after. And so the general strategy here is consider a new coordinate system where the hub is 0, 0. Then find the angle relative to, like in a regular coordinate system, you would have the x-axis as 0 degrees. And then you sweep around to 2 pi. So with the hub at the center of the coordinate system, find the angle to each of the radii endpoints, and then sort the list, supposing you place them in an order that kind of goes back and forth around the circle, around the hub, they will not necessarily be in order of their angles. So find the angle of every point and then sort them by their angle. Now you will have all your points in a known order that's useful for the algorithm, which is from point number I to point number I plus 1, take a vector, that vector from point number I to I plus 1. That's vector A. Then consider vector B from point I plus 1 to point I plus 2 within that ordering by angle. Well, now you have these two vectors and consider their cross product. It's going to have a cross product, either positive or negative, right? And one will represent a clockwise turn from one vector to the next vector, and the other, positive or negative, will reflect a counterclockwise turn. And so what we want to find is that all the z vectors have the same sign. That will, in fact, ensure that the polygon is a convex polygon. You can test that out manually with some polygons on paper if you wish. And so that is what's going on in this code here with this function getHub radii ring. We are going to get the angles from the hub for all the points. We're going to map arctan onto the coordinates of each point. Then we are going to sort them. Then we are going to turn these into, okay, we're going to call getHub radii ring. Okay, that's going to return a list. Then we're going to get a list of the z cross products. And then we're going to, this is kind of like a reduce. This is kind of like a map reduce algorithm a little bit. Okay, so z cross products I times cross products I plus 1. Well, this algorithm is going to determine whether the radii cross products vectors all have the same sign, because if you multiply a negative and a negative number, you get a positive number. If you multiply a positive and a positive number, you get a positive number. So by checking if the products of any two consecutive ones is a negative product, then you can ensure, going through the list like this, that they all have the same sign. Okay, so they all have the same sign. Then we're going to call this point in polygon function, which, look, we've got here a link, we've got the license. Well, that's just great. Now we're going into the draw method. So if we go to the program here, we'll hit done. We have a web. Look how it's drawn. Okay. For this part, I almost lost my mind. And the reason that I almost lost my mind was because I had this thing programmed to go from layer or level 0, the inside of the hub, straight out to the first radius strand, and then just around. And then when it got to the n-1 radius strand, it would jump out to the 0th radii strand at the next level outward. So this created an unsatisfying spiral. And it turned out that there is a more complicated but more satisfying algorithm to draw the spiral, which involves taking each radius by the number of spirals times around. You know what I mean? The number of laps around, complete cycles around the circle that will be accomplished along the length of one radius. How many times shall it go around? And then you divide the length of the radius by that number to get little segments. Then, when you go from the point on the previous radius spiraling around to this one, you will extend outward by a fraction of the length of the segment of the radius drawing to, equal to the number of this radius as a fraction of the number of radii that there are, which means that you start at the center of the hub, and then when you go to the first radius, you will go 1/n of the distance, where n is the number of radii strands. You will go 1/n of the distance of the first segment, where that segment is 1/m of the length of that radius. So this is different for each radius strand, where m is the number of laps the web is going to go around in total. So if it's going to make 10 cycles around, you're going to get 10 segments, and the distance that the web will go, the distance in that 10th of the radius that the web is actually going to cross is going to depend on where you started going through. Does that make sense? I think it makes sense. I think I've said that enough. So that even when you're on the first lap, you're going to start on the inside, but as you go around the web, you're going to go farther and farther out on that first lap until you get to the outside, and that's where it's going to overlap. So instead of going just in a circle all the way around and then jutting outward, it's going to gradually do it. And the purpose of this is that the path is more gradual and it's more natural. And that almost drove me insane programming that, because obvious reasons, I guess. So we've got that. Okay, pointed polygon is finally. Okay, so that's it. Oh, one more thing. Okay, let's talk about clockwise and counterclockwise. I was very lucky that this did not involve a major, undertaking to implement. It's pretty simple. I don't remember how it's done, and I'm not going to look at it because my head hurts too much right now from that explanation about the spiral. But let's talk about the spiral winding. This was simply to change the number of laps that occur. And so, as you can see here, this web spiral goes gradually outward. That's what I was describing. But how many times does it do that? It looks like 1, 2, 3, 4. Okay. 1, 2, 3, 4. Yeah, 4 times. Okay. So if we do tight, then we get, too many to count. Maybe it's 15. Maybe it's 12. Somewhere in there. Spiral droop. Now this one, luckily, was pretty easy. If you want it to be completely tight, you just draw a line from point A to point B. You determine where those points are, and then you just draw a line. But when you want it to droop, then instead you will use a different drawing function. You will draw a curve instead. And the way that that works is this. So you want to draw an arced line from this radius to this radius, like that, arcing. Instead of being a straight line, it's going to arc. How do you do it? Well, you still use point A and point B, but you're going to draw a curve that has a control point. So the curve will go through the control point. How do you find what the control point is? Well, you find the midpoint between point A and point B that you're drawing the line through. The midpoint is going to be on the line if it's a straight line, right? And if you want the control point to be inward more, then you are going to find the vector from the hub to the midpoint, and then you're going to scale it down. That's how it's done. And so what the spiral droop does is it configures the scale down of the vector to the midpoint, which is the control point for the quadratic line drawing function. And so that one I got off pretty easy on, as far as implementing that feature. I mean, there was still some, grinding of the gears in order to figure out how to do it, but it was relatively easy. And then once I did have a solution for how to do it, it was like, just reference one calculus web page about how to scale a vector down, and then off you go. 5 seconds to implement in the JavaScript. Okay, save image is built into the canvas, no work necessary. And that's it. Now you have a spider web. Ta-da! Congratulations. Happy Saturday.